Hi everybody. Today in this video we're going to be talking about review problems for acids and bases in general chemistry 2. So for the first problem here, an aqueous solution of 2.3 times 10 to the minus 2 molar of NaOH is added. Which of the following is true about this solution? What we know is that NaOH is one of our strong bases. And in this case, when NaOH is added to an aqueous solution, it's going to fully dissociate into Na plus and OH minus. And it's a full dissociation because it is one of our strong bases. And this is the same case if it was a strong acid as well, which it is not in this case. So since we're adding a strong base to our solution, or we're adding a strong base into our aqueous solvent, this is going to be a basic solution, not an acidic solution. So we can get rid of letter A. And technically, if you understand the idea of pH and pOH, we can get rid of letter C as well. Because when we're trying to find our specific solution here, we have the equation for pH and pOH, and the equation for pH, if you understand the idea of pH, this little p actually is a mathematical transformation, which means negative log of whatever is in front of the p, and then in this case, it's going to be H plus, or H3O plus if you're dealing with those specific substances. And in this case, we can actually find pOH directly because we have the concentration of OH minus. And that is because the full 2.3 times 10 to the minus 2 molar of NaOH dissociated. So the concentration of OH minus is going to be the 2.3 times 10 to the minus 2 molar of OH minus. When you do this calculation, you'll find that the pOH is actually going to be 1.64. And so we can tell that letter C was wrong to begin with. But the idea with pH, pOH and pH relate very easily, where pH plus pOH is equal to 14 in aqueous solutions. So if we wanted to find pH, it is just going to be 14 minus the pOH, well, we'll get an answer of 12.36. So we'll see that letter B is the right answer. Now, letter D we have to kind of think about too. It is asking if NaCl were added to the solution, it would change the pH. And this would only be true if our strong base dissociation would be in an equilibrium of sorts. So if it was a weak base, if sodium was our common ion, then we would actually have a shift back towards the left side or the reactant side to end up changing the pH because it would consume some OH. But in this case, since it is a strong base, simply put, our salt that we add won't change the pH at all. For this next problem here, a chemist decides to add 0.1 molar of NaCH3COO to a solution of 1.0 molar of CH3COOH. What best describes the reason why the pH of the solution actually increases? This is a common example of a buffer solution, where we have a weak acid, our CH3COOH, more commonly known as acetic acid. Whenever it's added to water, it will act as an acid. It will donate the proton to the water, making H3O plus, and then its counter ion CH3COO minus. This is the reaction that we would have for a weak acid. The chemist ended up adding 0.1 molar of NaCH3COO to this specific solution. Now, when this salt will dissolve in water, if nothing else is given in the problem, we assume a strong dissociation, and it will completely dissociate into Na plus its anion CH3COO minus. And in this case, as it fully dissociates, we'll have the same concentration of our dissociated counterparts, 0.1 molar. Essentially, since we're adding this CH3COO minus, this is a common ion into this specific above equation, where we're actually adding some CH3COO minus. And since we're adding something to one side, or in order to re-equilibrate, the reaction will shift towards the left side. Let me clarify that again. Because we added a common ion on the right side where we're adding something, the reaction will shift away from it in order to re-equilibrate, or it'll shift more towards the left side. And in turn, we'll actually have an overall decrease in H3O+, which will in turn increase the pH. So that is the full reason and fully thought out reason why the pH will increase when you add this common ion. And let's look through the answers in order to find that. NaCH3COOH donates OH minus to H2O. We know this is not the case because there is no OH for it to donate in this case, even though it is a conjugate base of the specific weak acid. B, Na plus changes the pH of the aqueous solution to the formation of NaOH. This will never occur because, like in the last problem, NaOH is a strong base, so it will never form NaOH in this aqueous solution. Letter C, the CH3COOH donates a proton to the salt. Now, if we kind of look to the specific idea here, it is donating a proton to the water to make the H3O+. So this is not the case as well, letter C. Letter D, the salts add a common ion that decreases the H3O+ concentration, and that is kind of what we derived before, where we have a reaction that shifts towards the left, and in turn decreasing the H3O+ and increasing the pH of our solution. So letter D will be our right answer here. For this next problem, what is the pKb for the conjugate base of the weak acid with a Ka of 1.3 times 10 to the minus third? And this will be an exponent here as well within the problem. So we know our Ka is 1.3 times 10 to the minus third. And what we need to know within a specific equation for finding Ka and Kb is that Ka and Kb will relate, where Ka times Kb will be equal to Kw. And this is the autoionization constant for dissociation of water. And so this has a specific constant of 1.0 times 10 to the minus 14. So if we wanted to find pKb, or Kb in this case for right now, Kb will just be equal to 1.0 times 10 to the minus 14 divided by 1.3 times 10 to the minus third. And after you solve that within your calculator, you should get a Kb of 7.69 times 10 to the minus 12. There is an answer that looks very similar in letter A, but this is only Kb. The question is asking for pKb. Now, again, you might not be given the full equation for pKb, but if you remember from pH and pOH, the p just means the negative log of whatever out is in front. So pKb is just the negative log of your Kb, or in this case, negative log of 7.69 times 10 to the minus 12. And you should get an answer of 11.1. And that's going to be letter C within this case. And again, this makes sense. There is another relationship. If you ended up finding pKa, you can do 14 minus pKa as well to give you pKb. So in this case, pKa is probably to be around 2.9. This is just another way of finding the same answer to the problem, just a different direction. The next problem, the pH at half the equivalence point for our titration curve is 5.5. What Ka value would correspond to the most effective buffer around this pH region? So the idea about titration curves is that we have an area of a buffer solution, we have an equivalence point, and then we have the end point. And this equivalence point tells you whenever all of your analyte has been completely reacted with your titrant. So this is our equivalence point. At half your equivalence, point is something very special where our concentration of our weak acid and our conjugate base are equal at this specific point, And whatever the rate of change is the rate of the change is almost zero, which indicates by this very, very low steepness part of the curve. And the idea for this specific point is that we want a pKa that is around this point to have the most effective buffer solution around this. A very well-known equation known as Henderson-Hasselbalch, the equation shows you that pH is equal to pKa of your solution plus the log of your conjugate acid, or conjugate base, sorry, divided by your weak acid. And this specific equation will tell you actually that whenever you're at half your equivalence point, since these two things are equal to each other in this fraction, we'll end up getting plus the log of 1. And if you take the log of 1 in your calculator, you'll end up getting that it is 0. So this shows you at this specific point, at half your equivalence point, pKa is equal to pH. So when they tell you the pH at half the equivalence point for the titration curve is 5.5, we want to find a pKa that is very similar to 5.5 because it is equal to your pH at this specific point. So if we take the pKa of every single option given to you within our multiple choice answers, we see that letter A is around 7.9, B is 1.2, C is 5.5, and D is 3.3. So the answer is going to be letter C. And the idea, the weak acid with the specific Ka value will be the most effective buffer around the 5.5 pH region. Let's look at this problem here. Which of the following would not shift the equilibrium to produce more products? So let's go through each of these answers one by one and to see which way they would end up shifting our reaction or equilibrium due to Le-Chatelier's principle. And so for A, what this is doing is adding NH4Cl salt. And if they don't give any information to you about how much the salt dissolves, you just assume it dissolves all the way, or it's a strong salt or a strong electrolyte, where it will dissolve into its cation, NH4 plus, and Cl minus. So when you're really dissolving NH4Cl into your solution, what you're really adding is NH4Cl, which is the most important thing here because it is in our equilibrium above. So when we add NH4, due to Le-Chatelier's principle, in order to reestablish that equilibrium after adding the NH4, in order to reestablish equilibrium by adding NH4, what you have to do is you actually have to shift away from the side that you added on. So this is going to be an overall shift towards the left, or towards the reactant side. So this is actually pretty indicative that A could be our correct answer. But let's go through the rest of the answers as well. With B, this answer is talking about decreasing the pH of the solution. And when you decrease the pH of the solution, you have to think about it as increasing the H3O plus concentration or decreasing the OH minus concentration. So here, we really care about the bottom one, the OH minus concentration, because that's what is in our reaction or in our equilibrium. So if we decrease our OH minus concentration, in order to make up for that lack of equilibrium or removing some of that product, it's going to shift towards the product side. So that is shifting it towards the product, so that can't be our correct answer because we're looking for the answer that doesn't. And so far, A is a very good potential answer. Let's go to letter C. Letter C is talking about adding HCl to the solution. So when we add HCl into the solution, this is one of our strong acids. So really we know it completely dissolves and forms H3O plus and Cl minus when it adds to water. There is no Cl minus within our equilibrium, so we don't have to worry about it, but we are increasing the concentration of H3O plus. And this is the same thing as letter B because we're decreasing the pH. So really we're going to have a shift towards the right as well. Because since we're increasing our pH, decreasing our pH by adding H3O plus, it's the same thing as decreasing OH minus concentration. Now let's look at letter D. Letter D is talking about increasing the temperature of the reaction. Here, we are not given enough information in order to make this decision, because what we need is the delta H of the reaction, or the enthalpy of this specific reaction, or the change in enthalpy. Because this enthalpy change will dictate if temperature change will shift it towards the right or towards the left. But we don't have that information, so we can't make that distinction. So we know B, C, and D are not the answer. Letter A is our correct answer for this specific question. When titrating a 1 molar solution of CH3COOH with NaOH, at the halfway point of the titration, which of the following main species are present? So again, when we go back to our titration curve, and we have this weak acid, let's say it looks something like this, where, and this is a very poorly drawn one, but this is our equivalence point and this is our endpoint. Halfway to our equivalence point is what we're going to be looking at right here, where the concentration, as before, of our weak acid and our conjugate base are equal to each other. So we know we're going to have both the concentration, or we're going to have both a major concentration of CH3COOH, acetic acid, and its conjugate base after it loses that proton. But now we have to look at the other answers to see what ends up happening. When we add NaOH to a solution, we know it fully dissolves into Na plus and OH minus. So after everything has happened, and after this specific solution has dissolved, there is no more NaOH in the solution. So what we can look at is that we either have Na plus or OH minus within our mixture. Interesting thing about titrations, especially at the halfway of the equivalence point up until the end point, is that all of the OH will react with H plus to form water. And this is true until the end point. So there is not going to be any OH minus within the solution, but we will have Na plus running around our solution as well, along with water, but usually these problems always indicate that water will always be present, so we don't need to include water. So we have our acid, our weak base, we have our acid, our conjugate base, and sodium ions running through our solution. So that's going to be letter B to look through our answer. So we have no OH minus in letter A. We have sodium, so C can't be the answer. And we have no actually H plus running through the solution as well, because all of the H plus, the majority of H plus will be reacting with the OH minus. So H plus is actually in a weak concentration because it's using a weak acid. So that's why letter B is going to be our correct answer here. And this is talking about halfway towards the end of the titration as well. If it was after the titration, there would actually be excess OH minus, so OH minus could be running around the solution as well over here. But we're not talking about that specific point. Referring to the previous problem, 100 milliliters of 1 molar solution of CH3COOH was fully titrated with 50 milliliters of a solution of NaOH. What was the concentration of the NaOH titrant? So this is really a conversion problem, because what we know is that all of the OH reacted with H plus. So what we know about acid and base chemistry is that all of the OH will react with the H plus, so the number of moles will be equal to each other. The number of moles of H plus or H3O plus is equal to the number of moles of OH minus. So what we have to do is find the number of moles of H plus, because we're given that amount of information, and see if we can find the number of moles of OH minus. So in order to find the moles of H plus, we are to look at our weak acid, and we have a 1 molar solution of CH3COOH. So we really have 1 mole of H plus, because there's only 1 proton for it to donate for every 1 liter of solution. Using a conversion table, we need to cancel out liters, and we're given that there's 100 milliliters of our solution. We know from previous videos that 1 liter will equal to 10 to the 3rd milliliters due to the prefix conversion. And so now we can get rid of liters, but now we have to cancel out milliliters somehow, and that's using the rest of the information of 100 milliliters. When we do our conversion here, we are shown that there is 0.10 moles of H plus that could possibly be present within the solution. Now we need to find the same thing for NaOH. For NaOH, we are told that there is 50 milliliters of this NaOH solution, and there should be a total amount of moles of 0.1 moles of OH. So we actually have to use this information in order to find a concentration. So we can use the same concentration table or conversion table in order to find it in molarity, where we know molarity is equal to moles divided by liters. So let's go through and do that. We know there is 0.10 moles of OH minus, and there is 50 milliliters. I'm going to put them under the same chart because that's what we're technically going to be doing with the equation. And it's not going to be 50 milliliters of NaOH because it fully dissolves into OH minus. So that's what we're going to be really focused on. And the reason why we're doing this is because the number of moles should be equal, so the concentrations will be different after everything is diluted, but really we're trying to see the number of moles fully react with each other as well. So if we end up doing the conversion here, where 1,000 milliliters again is equal to 1 liter, we end up getting that the concentration should end up being double that of the original concentration, which will be 2 molar. So letter D is our final answer here. For our last problem here, what is the pH of a 0.05 molar acetic acid solution with a Ka of 1.8 times 10 to the minus 5? So we need our Ka in order to find our pH due to it being a weak acid. And the important thing about finding a pH of a weak acid with the Ka is that most of the time, 99% of the time, we're going to need to use a nice table where we need to write out our reaction of acetic acid with water, where acetic acid donates a proton to make H3O+, and our conjugate base, CH3COO-. And all of them will be aqueous except for water, which is going to be our liquid in this case. And anytime you have an ice table, you're going to write out your chemical reaction up top. You're going to write your initial change and equilibrium lines. And the only phases that you're going to include are going to be aqueous and or gases. So we're going to get rid of our liquid lines here. And with this problem, with the information given to us, any information they usually tell you, unless it's specifically at equilibrium, will be in our initial line. So the 0.05 molar will go in our initial line for our acetic acid. And the only things you can put within our boxes are pressures or concentrations in molar, which is the big M. And unless told specifically otherwise, the other concentrations will be 0 initially. For the change line, the reactants will be negative and the products will be positive. All of the coefficients in the balanced chemical equation will come down as well. So it's going to be -1, +1, and +1. And then the last thing is the amount that you change by, which is going to be X. X will be included in every single change line. The only thing that differs is the sign and the number in front, depending on your balanced chemical equation, and if you're a reactant or product. The equilibrium line is pretty simple. It's just adding everything down in the column. So for the equilibrium line, it will be 0.05 minus X. It will be plus X and plus X as well. So this is our equilibrium line, or concentrations at equilibrium for all of our species. The important thing with this is that we can actually find our K constant, or our Ka, with relationship to this. And that is going to be the ratio of our concentration of our products, which is H3O+, and our conjugate base, divided by our weak acid, CH3COOH, at equilibrium, because you can only use concentrations at equilibrium for your K constant. So let's plug those in from our equilibrium line. We have just X squared divided by 0.05 minus X. And it's equal to our Ka, which is given to us in our problem. The reason why I'm doing this is because we need to find X in order to find our pH. Because pH, remember, is going to be negative log of our H3O+ concentration. And this is going to be the H3O+ concentration at equilibrium, which is just going to be this box here. which is just x. So if we can find x, we can find our pH of this specific weak acid solution. Now, within your lecture class, there might be some approximations that you make, and we're going to make that approximation here. And the reason why we can make this approximation, which I'm going to write up in the top right, is because the concentration of our weak acid divided by our Ka is greater than 100. Other classes might have other standards, but this is what we're going to use for this video here. And with this approximation, we can cancel out the minus x in our denominator. So now we have an easy way to solve for x, where x squared is equal to 1.8 times 10 to the minus 5 multiplied by 0.05 from the denominator, which is just equal to 9 times 10 to the minus 7. And so when you take the square root of both sides, you'll end up getting that x is equal to 9.49 times 10 to the minus 4th molar. And since this is just our concentration of H3O+, we could plug it into our pH equation. And our pH is just going to be the negative log of our x, or 9.49 times 10 to the minus 4th molar. And so we get pH is just going to be 3.02. I hope you all have learned something from this video, and please check out my channel for more chemistry and math related videos.